Thank you. Hi, everyone. Today I'm going to be talking about lunar farsides, basically how it will open up new cosmic frontiers for us. Okay, Perfect. So I'd like to say there are a few uniquely challenging questions that require low-frequency observations from the far side, one of which is hydrogen cosmology, which Stephen touched on. Basically, looking at the dark ages of the universe, and the signal from it is at low frequencies, below 40 megahertz. The other unique science case is Magneto-spheres, a study of exoplanets. Let's go over that little bit of a detail because we haven't looked at it yet. So to stress the point of how useful the study could be, I'm going to use one animation produced by Chuck Carter at Caltech. If I can play it. Yeah. So in this animation, there are two scenarios. In both the scenarios, there's a host star emitting CMEs, coronal mass ejections. On the left, it interacts with the planet without a magnetosphere. On the right, it's a planet with the magnetic field. The first thing you'll notice on the right, other than the blue magnetic field indicated, is the auroral emission. Associated with the auroral emission that we know and love with the green in the clouds is also radio auroral emissions. So thereby, if we think about it carefully, if we can look for radio emissions from planets, we are probing planets that have magnetic fields. So if they have magnetic fields, they are possibly protecting atmospheres of the planets from any energetic particles coming from the host star. That way, we could be answering and looking for planets with habitability. So that is radio observations. But again, you can ask me at what frequencies, where do we tune the dial for these radio observations? To answer that question, we can look at radio auroral emissions from planets in our solar system, which is what I'm showing you on the left. The left is frequency versus the strength of the radio flux for planets from our solar system. The main takeaway from there, all those frequency emissions are below 10 megahertz, except for Jupiter, which has emissions up to 40 megahertz, nonetheless still less than 40 megahertz. If we use similar scaling laws and apply the magnetic field strength to known exoplanets, this is what I've done on the right, and then again, main takeaway, the expected radio flux from these possibly habitable planets are less than 30 megahertz. Hence, for both the science cases, the one that Stephen spoke about, the hydrogen cosmology and radio exoplanets, we need low-frequency observations, which needs lunar farside, the only radio-quiet zone in our solar system. I will stress this point once more, because if you want radio observations less than 30 megahertz, ionosphere blocks them. You cannot do it from Earth. You could say, okay, let's just go to space. But for both the science cases, we need really sensitive measurements. So we need hundreds of elements in the array. Let's find the nearest surface. You've gone to the near side of the moon. You've gone all the way to the near side of the moon. You're still going to see interference, which is what Judge showed. So you might as well go to the far side. And I like to drive that point home with this plot from NASA's RAE2 from 1975. If nothing else, I want to update this plot. I'm tired of showing the 70s plot. But this plot is exciting because, so this is time on the x-axis and the strength of radio flux on the y-axis for different frequencies below 11 megahertz. The thing that I marked with the red arrow is the immersion point. It's when the orbiter goes to the far side. And you can see exactly when it enters the far side, it's a flat. It's really quiet. And I hope we still keep it that way. Okay, with that in mind, a few of us in the community have come up with a few radio array concepts. I'm going to be first talking about far view. Far view is a concept or an idea to put a radio observatory on the far side of the moon, but by in situ manufactured elements. So we will use the regolith metals in the regolith to actually manufacture the individual dipoles. FARView is currently in NIAC Phase 2. It's a funded NIAC Phase 2 project. Now, a few overview properties about FARView. It'll operate between 5 to 50 megahertz to look at the dark ages. And what is the elements going to be? At such low frequencies, the construction of these radio antennas are simpler. They're just simple dipoles, which is what Lucy Knight is using as well. You can think of just electric rods. And FARView is suggested to use about 10-meter long dipole antennas. The ultimate goal of FARView is to give you a tomographic map of the universe during the dark ages. To make that happen, calculations show that we need about 100,000 dipoles, which is why we are doing it in situ. It's a huge number. Okay, so operation-wise, we will operate during lunar day, we will do solar observations, and lunar night, we will do the dark ages observations. Okay, what makes FARView feasible is our collaborators at Lunar Resources, basically. So they are developing technologies such as molten regolith electrolysis to extract the necessary elements to create both the solar cells and all the electrical components like the dipoles, power lines, and preamps for the antenna, for the telescope. Now, in the science team, we worked out what the FARView array configuration should be like. What do I mean by array configuration? How you're going to place and where you're going to place these 100,000 dipoles. We do that by answering two questions. Do we have the sensitivity to detect the signal? To answer that, it so happens you need to keep them dense. You need to keep the dipoles or the elements together, which is why there's a central core. Now, the second question we need to answer, okay, we have the sensitivity, but do we have the capability to detect the signal given our galaxy is loud? At the same frequencies of below 50 megahertz, our galaxy is loud as well, but our signal is really faint. So we have to remove the galaxy from that data. For that, it is what we call the foreground mitigation. For that, we need our dipole spread out in a halo and long baselines. So we have a configuration called the core halo configuration. Now, we know the general idea, but to give us some numbers, our collaborators at Brown University, Willow here, who has a poster, has detailed that the 100,000 dipoles, the core should have 80,000 and the halo should have 20,000. The numbers work out like that. Further things that we've figured out, let's divide the 100,000 dipoles into clusters of 570 each, which will make one power unit. Another division that we've done is actually correlating all of these 100,000 dipoles signal is a massive task. So what we do is actually beamform every 16 units. So now we have 6,000 unique pairs to cross-correlate. So the data rates become manageable. One more advantage, now you have multiple beams on the sky. I like to think like multiple eyes on the sky with the same array. And that becomes useful for the radio, for the exoplanet studies. So you're having something that's called the panoptic survey. Okay, the other thing we did with the NIAC funding was select potential build sites. We formed a table of 12 selection criteria. The first two you all can guess is one of them is we need to be on the far side. That's our main criteria. We need a large enough area. This whole telescope extent will be about 14 kilometers, so large enough area. The next 8 criteria are surface properties like Stuart spoke about. So basically surface roughness, what's the slope, are there too many boulders nearby? Given all of that, we have identified 17 fully viable build sites. I want to end off saying that yes, FARView seems a little futuristic, but still possible in the 2030s. But before going there, I think we could go with few smaller steps, a precursor mission. And the same collaboration had put together this concept study also funded by NASA. We could start with this as a possible precursor mission, which is the FARSIDE. FARSIDE's mission concept will also have a central lander by the clips and a base station. Here are the important differences. We will carry the antennas to the surface because the number of antennas on this mission are only 128 pairs. And the way we will deploy these antennas are with the 4 rovers indicated in this mission concept. So the rovers, each of the rovers are single axle rovers developed by JPL. The rovers will carry tethers, which are the orange or yellowish rope you see coming out of the lander. Below the tethers will be embedded the antennas. So these are simple dipoles literally embedded inside underneath the tether. So the rovers will roll it out, lay it out in the configuration. The configuration we came up for this is a spiral arm. And the exciting part about this is we have a couple of heritage we can take from. So it draws from the Apollo 17 heritage with the tether technology and also the dipole placements. With that, I'm going to put up my summary. And I think I want to leave one point up, stress one point. I think the questions we're trying to answer with putting radio telescopes on the moon are definitely Nobel Prize worthy winning. Because don't we all want to know, is there life on other planets or when and where did the first stars form? Yeah, thank you.